So what's the real difference between a samurai sword and a cast iron skillet? I mean, think about it. One is flexible, razor sharp, the other is heavy and brittle. But here's the crazy part. They're both made of the exact same things, iron and carbon. So what gives? Well, the secret isn't in the ingredients, it's all in the recipe. And today, we're going to open up the master recipe book that literally defines the entire world of steel and iron.
Here's how we're going to tackle this. We've got 5 quick sections. First, we'll meet our main characters. Then, we'll see how they get together to form alloys. After that, we'll pull back the curtain on the map of metal itself, check out the most critical transformations, and finally, you'll know for sure what separates steel from cast iron. It's a really straightforward journey, I promise. All right, let's dive in. Section 1, the main characters. You know, this whole story, it's basically a two-man show. You've got iron and you've got carbon. And believe me, the way these two interact, it's the foundation of, well, pretty much everything in our modern world.
So think of iron as our lead actor. It's super versatile. Its big superpower has this fancy name, allotropy, but all that really means is it can completely change its internal shape, its crystal structure, just by getting hotter or colder. It's like a shapeshifter. And carbon? Oh, carbon is the magic ingredient. It's like the spice in a recipe. Just a tiny, tiny pinch can totally transform iron, taking it from soft and easy to bend to unbelievably hard and strong.
So check this out. Here are iron's two main costumes. Below about 910 degrees Celsius, you've got what's called alpha iron. Picture its atoms in a box, one at each corner and one right in the dead center. Pretty compact. But crank up the heat past that 910 mark and bam, it rearranges itself into gamma iron. Now the atoms are at the corners and in the middle of each face of the box. And this new setup, it leaves more empty space between the atoms. Why does that matter? Well, it's absolutely crucial, because that extra space is where carbon can sneak in. A lot more carbon. And that one little detail, it's the key to this whole story.
Okay, so we've met our two elements. Now for the fun part. What happens when they actually team up? In the world of metals, we don't just call them mixtures. We have cooler names, phases or microstructures. Think of them as different teams, and each team has its own unique skill set.
First up on the team roster is ferrite. This is the most basic combo. It's just a little tiny bit of carbon dissolved into that low-temp alpha iron we just talked about. And since there's hardly any carbon, ferrite is exactly what you'd expect. Soft, ductile, meaning you can bend it, and magnetic. It's really the foundational building block for most simple iron.
All right, next up, austenite. Now this is what happens when you dissolve carbon into that high-temperature gamma iron, the one with the more open structure. And because it's more open, austenite can hold a ton more carbon. We're talking up to about 2%. Now this stuff only exists when it's really hot, but, and this is a big but, it's the critical starting point for making almost every strong steel you can think of. Okay, now meet cementite. And this one's a whole different beast. It's not just carbon dissolved in iron. Nope. This is a true chemical compound, Fe3C. That means 3 iron atoms are chemically bonded to 1 carbon atom. It's a fixed recipe. And because of that, its properties are totally distinct. The one thing you need to remember about cementite, it's crazy hard and also pretty brittle. Honestly, you can think of it like little bits of ceramic mixed in, and its job is to add hardness. So, what do you think happens when you take the soft, bendy stuff, ferrite, and you mix it with the super hard, brittle stuff, cementite? You get something amazing called pearlite. And this, right here, shows you the magic of microstructures. See, pearlite isn't just one thing. It's this beautiful, layered structure, almost like a metallic plywood. You have a thin layer of soft ferrite, then a thin layer of hard cementite, and so on. This combination, this is what makes pearlite both tough and strong. It really is the secret sauce for awesome steel.
Okay, quick recap. We've met our players. Soft ferrite, high-temp austenite, hard cementite, and the super combo, pearlite. Now, it's time to show you the game board where all the action happens. Let's unveil the map of metal.
But wait a second, how does anyone actually use this? I mean, if you're an engineer, or even an old-school blacksmith, how on earth do you know what's going to happen? How do you know what structure you're going to get if you take, say, 1% carbon, mix it with iron, and heat it up to 1,000 degrees?
Well, there's a tool for that, and the answer is the iron-carbon equilibrium diagram. This is the master recipe book, the secret map we've been building up to. It tells you with absolute certainty which phase, or which mix of phases, you're going to find at any temperature and any carbon percentage. I'm not exaggerating when I say this is one of the most important diagrams in all of engineering.
period. So let's build this thing, piece by piece, and trust me, it's way less complicated than it looks. The up and down axis, the y-axis, that's just temperature. Hot at the top, cold at the bottom. Easy. The side-to-side axis, the x-axis, that's just how much carbon we're mixing in. We start with almost no carbon on the left and go all the way up to about 6.5% on the right. Okay, axes are in place. Now we can start drawing the borders and mapping out the territories where our different phases live. Way up high, in the high temperature zone, that's the kingdom of austenite. Down in the bottom left corner, low temp and low carbon, that's ferrite's home turf. And as you start moving to the right, as you add more and more carbon, that's when our hard buddy cementite shows up and really starts to take over. And right away, just by looking at this map, it splits into two giant families of metal. Look at this line right around the 2% carbon mark. Pretty much everything to the left of that line, with less than 2% carbon, we call that steel. Everything to the right with more than 2%, that's cast iron. Just one simple line on a chart separates two materials that behave in completely different ways. All right, now for what I think is the coolest part of this map, the lines themselves. These aren't just random borders between territories, no way. Each line represents a transformation. It's a point where, if you heat or cool the metal past it, the entire internal structure flips and becomes something new. You'll see a few big horizontal lines on this map. These are the critical temperature reactions. The one way up top we can kind of ignore for now, it's not as industrially important, but the two we really need to focus on are the eutectic reaction at 1147 degrees C, that's the key for cast iron, and the eutectoid reaction down at 723 degrees. And that one, oh man, that's the real secret to making incredible steel. Let's just pause on that for a second. 723 degrees Celsius. Write that number down. It is, without a doubt, one of the most important temperatures in the entire field of metallurgy. So, let's zoom in and see what makes it so special. This specific spot, at 723 degrees and exactly 0.8% carbon, is called the eutectoid point. Imagine you have a piece of steel with that exact carbon amount. When it's hot, it's all austenite, right? Now you start cooling it down, slowly. And the moment it crosses that 723-degree line, poof, the entire thing transforms all at once into 100% pearlite. You get that perfect, strong, layered structure we talked about. This is it. This is how you make the ideal, strong, tough base steel. Okay, now let's jump back up the map to that other line, the eutectic reaction. This happens at a much higher carbon content, about 4.3%, and a hotter temp, 1147 degrees. And here's the cool thing about this specific mix. It has the lowest melting point of any iron-carbon alloy, period. As it cools, the liquid metal turns solid all at once into a mix of phases. And that low melting point is exactly why we call it cast iron. It's super easy to melt down and pour into a mold to make complex shapes, like a skillet. All right, let's bring it all home. We've met the players, we've studied the map, so how does this all translate into the real world? How do we use this to actually make things? This table basically spells it out. Let's look at the steel family. If you've got less than that magic 0.8% carbon, your final product is going to be a mix of the soft ferrite and the strong pearlite. If you nail that 0.8% mark exactly, you get 100% strong pearlite. And if you go over that amount, you still get pearlite, but now you have extra bits of that super hard cementite floating around, which makes the steel even harder, but you guessed it, also more brittle. It's the same idea over on the cast iron side. By just picking our carbon percentage, we're basically choosing a spot on this map to land. And that lets us perfectly dial in the properties we want for the final product.
So you see, this thing is so much more than just a chart for engineers. It's literally the map that unlocked the modern world, from the Iron Age right through the Industrial Revolution. It's what took us from blacksmithing being a kind of mysterious art to metallurgy being a precise science. Which kind of makes you wonder, right? What are the new maps being drawn today? What do the diagrams for composites or graphene or advanced polymers look like? What new materials map will define our future?